Welcome back to this next video in which we are discussing the transportation of oxygen and carbon dioxide in the bloodstream. Okay, so up here we have what we did in the previous video, which is that we looked over the basic understanding of how oxygen and carbon dioxide are transported in the bloodstream, and we saw that carbon dioxide is lower in the arterial system than it is in the venous system. And a very important point that I'll stress again is that carbon dioxide is at a low here, but it's not the case that there's no carbon dioxide in the arterial blood. There is a lot of carbon dioxide in the arterial blood. It's just that it's at a lower level than it would be in the venous blood. And similarly, there is a differential in oxygen concentration in the arterial system compared to the venous system. We have high oxygen in the arterial system and low oxygen in the venous system. But again, you do not have no oxygen in the venous blood. You have a lot of oxygen in the venous blood. You just have more in the arterial system. And the difference is how much has been unloaded to the peripheral tissues. Okay, so we're now going to begin the more in-detailed discussion of the transportation of oxygen and carbon dioxide around the bloodstream, and we're going to begin with carbon dioxide. And I justified this at the beginning. The reason we're doing it this way is because to understand the transportation of oxygen around the bloodstream, in particular to understand the Bohr shift, we need to know about the transportation of carbon dioxide. Okay, so I'll put the title up here then. We are going to start off with carbon dioxide, CO2 then. Okay, so where do I want to begin the story? Well, I actually want to begin the story by discussing carbon dioxide that is present in the arterial blood. That's where I want to begin the story. How much carbon dioxide is present in the arterial blood? Then we'll follow the story through the peripheral capillaries and we'll see how much carbon dioxide is added. We'll have a look at the venous blood and then we'll go up to the pulmonary capillary and see how it then is taken out, and then of course we're back to the arterial system blood. But let's begin then with carbon dioxide in the arterial system blood. Okay, so there is carbon dioxide in the arterial blood and it's in the blood dissolved. So you have carbon dioxide molecules dissolved within the water molecules that make up the blood. Okay, so let me start by telling you about the concentration of carbon dioxide that is dissolved in the arterial system blood. So the concentration of dissolved carbon dioxide in the arterial system, so I've put square brackets around carbon dioxide here to indicate that I'm talking about concentration of carbon dioxide, and this A here is indicating that I'm talking about in the arterial blood. It's around 1.2 millimolar, so 1.2 millimoles per litre of blood. Now, when people talk about the concentration of a gas such as carbon dioxide that is dissolved within the blood, they often do it in a different way. Instead of giving a very basic concentration like this, and this is the thing that to most people makes most sense, to just give the concentration of dissolved carbon dioxide, because everyone knows what this means. However, people often don't do it this way. Instead, the way they communicate the concentration of carbon dioxide that is dissolved in the blood is by giving you a partial pressure of carbon dioxide. And I just want to explain what people mean when they say there is this partial pressure of carbon dioxide in the arterial blood. So people will say something like this: the partial pressure, so P for pressure, and then we'll subscript it little a for arterial, and then we'll have CO2 like so. So this means the partial pressure, and I'll just write down in full what this means. It means partial pressure of CO2 in the arterial system. But I'll just put partial pressure, that's the key bit that you might not have seen before. So this just refers to the pressure generated just by CO2 molecules. So of course in a gas normally, for instance in air, there are loads of different types of molecules. There are nitrogen molecules, and of course nitrogen makes up most of the air, 79% I believe. So dinitrogen, nitrogen triple bounded to another nitrogen atom, those molecules make up most of the air. But you also have lots of other molecules in, so oxygen molecules as well, oxygen double bound to another oxygen atom, and then other gases such as carbon dioxide, a little bit of argon, which is just a noble gas and is just the atom, etc. So you have lots of different types of molecules. The partial pressure refers to the pressure that's generated specifically by carbon dioxide molecules. And it's a concept that is about gases, not about gases dissolved in fluid. So what am I talking about saying a partial pressure in arterial blood? This is a concept from, gas chemistry or gas physical chemistry. So what am I talking about here? Well, the reason people give this is that they are talking about the partial pressure of CO2 that would need to be present in order to give rise to this concentration of CO2 in arterial blood. So I'm just going to explain something to you called Henry's law. So I'll change colour again. So Henry's law is a really important concept here to understand why people talk about an arterial partial pressure of CO2. So this is a law, a very basic law, which is why medical students can cope with it, from physical chemistry, that tells you how much, what concentration of a gas you will get dissolved in a fluid, such as blood, if you expose it to a certain partial pressure of that gas. So let me just draw a little picture for this. So the best way to illustrate this is to imagine having a little beaker here, and this little beaker is going to contain some sort of fluid, and we can imagine that this might be water. So let's just make it very basic, and we can imagine that this is water, but of course we're interested in blood as our fluid. So here is water, and if you expose this beaker, if you expose this fluid here, the water, and I might just colour the water in blue. So here is the water here in blue. But you can see that the water is in contact with gas up here. Here is the air, or whatever gas it's being exposed to. It might not be normal air. Okay? Now, if this gas up here that the water is exposed to contains a certain partial pressure of CO2, and remember, pressure is really comparable to concentration. It's more complicated than concentration, but it's dependent on temperature. Really, it's the amount of force that the gas molecules are exerting outwards, if you imagine putting a little box around them. And it's the force per unit area of that box. However, effectively, it's kind of a measure of concentration. It also takes into account temperature, because of course temperature affects the energy of the individual molecules, and therefore how hard they'll bang on the container. But if you keep temperature constant, then pressure is all about just the concentration of those molecules, and of course that will affect the force that will be exerted on the box, because if there's a higher concentration, there's more molecules going to be hitting the surface of the box. Okay, so we're now going to imagine that we have a certain partial pressure of carbon dioxide up here, and I'll just write that on. Get another colour black. I'll go for green now. So imagining that we've got a certain partial pressure of CO2 up here, and because I'm not talking about the arterial partial pressure of CO2, I've not subscripted the A there, I've just put PCO2, referring to the partial pressure of CO2. What's going to happen is, if we've got carbon dioxide molecules in the gas that this fluid is exposed to, so here's a carbon dioxide molecule, some of those carbon dioxide molecules are going to end up dissolving in the water, and Henry's law is a way of taking in the partial pressure that this air that the water is exposed to, and remember, the air that's in this bit immediately above the water is in equilibrium with all of this air around the beaker, so you've got loads of this air, okay, and it's, redistributing, so it's not always going to be the same air that's over here, all the air molecules are moving around so that everything's continually in equilibrium. So what I mean by that is that when we remove CO2 molecules from the air originally right above the water so that they can go into the water, it will then redistribute so that the partial pressure of CO2 remains the same. We're imagining that, we've got a huge amount of air here, so the actual overall change to the partial pressure of CO2, because CO2 molecules have gone into the water, is utterly negligible. Okay, so we can assume that the partial pressure of CO2 remains constant, and Henry's law is a very simple mathematical relationship to tell us, if I have a certain partial pressure of CO2 in this air, what is going to be the concentration of carbon dioxide in this water once it's dissolved? And It's a really simple mathematical relationship. It could not be simpler. This is Henry's law then, and I'll go back to the red pen since I originally put the title in red. So Henry's law says that the concentration of CO2 that you will end up with inside this beaker here is going to be equal to some solubility constant, and if you like, you could subscript this CO2 because it's going to be the solubility of CO2. So this is a constant number, so I'll just put that in. This is a constant. However, of course, it will depend on certain things. It will depend on what fluid we're talking about. So we're talking about water here, but if we're talking about blood, it will differ potentially. And it will also depend on temperature. The solubility of carbon dioxide in water depends on what temperature the water is at and what temperature the gas is at. So other thermodynamic parameters are important here. Of course, when we're talking about blood, we will be talking about blood as the fluid, and we'll be talking about 37 degrees Celsius body temperature. Okay, so the solubility, which is a constant provided that temperature and the fluid are staying the same, which we can assume they are, times the partial pressure of CO2 in the gas. Now, that is an extremely simple relationship. It's a linear relationship, okay? If this goes up, this goes up. If this doubles, specifically if this doubles, this will also double. Very simple linear relationship, okay? And here is the gradient of, if you like, that straight line graph relating the partial pressure of CO2 to the concentration of CO2. Okay, right. So this is why partial pressures of CO2 in gases relates to the concentration of CO2 in a liquid. This is Henry's law. Coming back to why we can then talk about an arterial partial pressure of CO2, what this means is it means what partial pressure of carbon dioxide would I need to expose my blood to in order to get this concentration of carbon dioxide in the arterial blood. So that's why we can move from using an actual concentration of carbon dioxide in the arterial blood to talking about a partial pressure of the carbon dioxide in the arterial blood. We're saying effectively, what if we had this simple setup, what partial pressure of CO2 would you need in order to get this concentration of carbon dioxide in the blood? Okay, now let me give you the actual solubility of carbon dioxide in the blood. So this constant has a value if we're specifically talking about blood. If we're talking about blood and we're talking about body temperature, so at 37 degrees Celsius, then the value of this solubility constant is 0.03 millimolar per millimeter of mercury. Okay, so you will find that in biology, in medicine, when we're talking about pressures, we always generally use millimeters of mercury as the units for pressures rather than pascals or atmospheres. And then here is our concentration, millimolar. So this is just telling us for each millimeter of mercury that you have in pressure, in partial pressure of CO2, how many millimolar, how many of these concentration units will you get dissolved in the blood at 37 degrees Celsius. So we can now work out what the arterial partial pressure of carbon dioxide is, because we know that the arterial concentration of carbon dioxide is 1.2 millimolar, so we can put that in there. We know that this solubility of carbon dioxide at 37 degrees Celsius in the blood is 0.03 millimolar, so we can now work out what the partial pressure of CO2 we'd have had to expose the blood to in order to get that concentration of carbon dioxide dissolved in the blood. So all I need to do is take this number here and divide it by this number, and if you do that, you'll get 40. Okay, so if I took 40, multiplied it by this, times this by 10, it will get to 0.3, and then times it by 4, which is equivalent to multiplying the whole thing by 40, we then get 1.2 millimolar. Okay, so let me just write that down then. So the arterial partial pressure of carbon dioxide then is 40 millimeters of mercury. Now, That explains why you can do this. It doesn't really explain why you would want to do this. So there's why you can do it. Why would you actually want to do it then? Well, the reason that you might actually want to do this is that everyone agrees on what units to use for pressure, millimeters of mercury, whereas with concentration there is a huge scope of different units that you could use. Here we've used a very nice one, the one that chemists like, millimoles per litre, but there are lots of different ways of talking about the concentration of gas dissolved in blood, and we'll see actually when we come on to discuss oxygen transport within the bloodstream that people use a different unit of concentration when we're talking about oxygen dissolved in blood compared to when we're talking about carbon dioxide dissolved in blood. So I hope that will give you a little bit of a flavour for why it's easier just to talk about the partial pressure of carbon dioxide in the arterial blood than it is to talk about the carbon dioxide dissolved. Because once you've given me this, I then know, okay, the actual concentration of carbon dioxide dissolved in blood, in theory I could work it out from this, because it would just be how much carbon dioxide would you get in the blood at 37 degrees Celsius if it was exposed to a gas with a partial pressure of CO2 of this value. So in principle I can go from this to this, and then I don't have to worry about all the different units that you could use for concentrations of gases in the blood. Okay, so there's a sort of explanation for why you might actually want to do this. Right, so where do I want to go now? One more comment about this. If this is the arterial partial pressure of CO2, 40 millimeters of mercury, what does that actually mean with regards to what the alveolar partial pressure for CO2 is? So another important concept here is the alveolar partial pressure of CO2, and this is written P subscript capital A, so note here the difference between this one and this one. This is a lowercase a, and this means the partial pressure of CO2 in the arterial blood, which of course means the partial pressure of CO2 that you'd have to have in a gas that the blood was exposed to in order to get the concentration of carbon dioxide dissolved in the blood that is present. Whereas this one, with the capital A, this means the actual partial pressure of CO2 in the gas that is in the alveoli. But of course, these two things are going to be equal to one another because the arterial blood has just come from the pulmonary capillaries. So how much CO2 is now dissolved in this blood? Well, it will be the amount that will be in equilibrium with the partial pressure of CO2 that is in the alveoli. So in fact, alveolar partial pressure of carbon dioxide is also 40 millimeters of mercury. So these two things are the same, but they have slightly different meanings. They have the same value, but they do have slightly different meanings, and you should distinguish between them. This is a more theoretical concept. This is a solid concept. This means the actual partial pressure of carbon dioxide in the alveolar air. Right, so we still haven't actually discussed the transport of carbon dioxide in the bloodstream. We're just discussing carbon dioxide dissolved in the arterial blood, and what I've told you is that we have carbon dioxide dissolved in the arterial blood, specifically this concentration, but we prefer to talk about the partial pressure of carbon dioxide in the arterial blood, which is 40 millimeters of mercury. Okay, and this is the same as the partial pressure of carbon dioxide in the alveolar airspace, and that's no coincidence. That is for good reason. So I will just put down here that this is also 40 millimeters of mercury. Right, so carbon dioxide is going to be dissolved in the arterial blood. The next thing that I want to talk about is the fact that carbon dioxide dissolved in the arterial blood is going to be in equilibrium with bicarbonate. So there is a dynamic equilibrium, there's a reaction that occurs in blood which is going to reach an equilibrium, and this is the conversion of carbon dioxide and water into a bicarbonate molecule and a proton. So let me now discuss this, and I'm just going to make myself a little bit more space. I would quite like to keep that in view, so I'll bring, what can we do away with? We can do away with Henry's law, so I think that's probably going to be the best compromise. So we'll now get another colour. We'll go to white, I think, for a while. Okay, so Let's now talk about this equilibrium. So we've discussed the fact we have carbon dioxide dissolved in the arterial blood, and we know the concentration of carbon dioxide dissolved in the arterial blood. Now, carbon dioxide molecules that are dissolved in blood can react with water molecules that are, of course, part of the blood. And this is the reaction that can occur. So carbon dioxide, CO2, plus a water molecule, and I'll discuss in detail what is actually happening here. So plus a water molecule, so plus H2O, and I apologise for that, didn't mean to do that. This is going to be in equilibrium, a dynamic equilibrium, with bicarbonate molecules, which has this formula, HCO3-, plus a proton, which will be given up to free solution. So the key one that you might not know the name of, but hopefully you do know the name of, is this molecule here, which is the bicarbonate ion. So this chemical reaction does not go to completion, okay? It is not the case that all the carbon dioxide dissolved in the blood will react with water molecules to create these two molecules. No. Instead, this is a reaction that reaches an equilibrium. The reverse reaction can also occur here. Bicarbonate molecules will combine with protons to reform carbon dioxide and water molecules. So it reaches a dynamic equilibrium. And in the arterial blood, the concentration of carbon dioxide will be in equilibrium with the concentration of bicarbonate and the concentration of protons, i.e. the pH. Okay, so firstly let me just discuss this reaction in a little bit more detail, then let me tell you the actual concentration of bicarbonate and protons in the, well, not protons, but pH, of course, from which you could get the concentration of protons in the arterial blood, to complete off. And then we'll actually go on to discussing transport of carbon dioxide around the bloodstream. Okay, right. So how does this reaction actually occur? Well, let's draw some little diagrams for this. So firstly, let's draw a molecule of carbon dioxide. So here is a molecule of carbon dioxide. Of course, it's a carbon atom double bound to oxygen twice. Let's now have a molecule of water, which I'll do in blue here. So here's a water molecule, oxygen bounds to two hydrogens, and both of those bonds are single bonds. So these two molecules here can react with one another, so I'm showing the forward reaction, and before they actually become bicarbonate and protons, they will form an intermediate molecule known as carbonic acid. So let me show you carbonic acid. So I'll try a new colour. So the way that this is actually going to occur is, and this is not an electronic flow diagram by any means, so chemists look away at this point, but a simple way that you can understand how this reaction is going to occur is you can imagine breaking one of the bonds between a carbon and an oxygen in carbon dioxide. So imagine breaking one of these bonds, let's say this one here. You don't break both of the bonds in the double bond, just one of them, and imagine giving one electron back to the carbon and one electron back to the oxygen. And I'll stress again, this is not an electronic mechanism, this is just to try and help you understand what's happening and keep track of all the electrons. Now, go to the water molecule and break one of the bonds between the oxygen and the hydrogen. Let's break this one. And again, imagine giving one electron back to the hydrogen and one electron back to the oxygen. So this hydrogen, this oxygen, this carbon all have free electrons now to bind. What we will do is we'll bind this oxygen to the carbon and we'll bind this hydrogen to the oxygen. And let me draw you what you will end up with. And I'll find, oh, I've got a new colour. Okay, so you will have the carbon here. Then it's still double bound to one of the oxygens because we didn't break this double bond here. Now it's going to have two single bonds to oxygens, and both of those oxygens are going to have hydrogens attached to one another. Okay, so this is the intermediate molecule that you get, and you will recognize that everything is happy here. Every atom has the correct number of bonds that it likes to have, and this molecule has a name. It's known as a carbonic acid molecule. Now, this is an intermediate step, okay? Whenever a carbon dioxide molecule and a water molecule react together in this reaction that I've drawn up here, they do form a carbonic acid molecule in the middle. However, it's not a stable molecule, so it's not going to be long-lived at all, and it's going to go very quickly. So what it very quickly breaks down into is bicarbonate and protons. Now, how does that occur? Well, quite simply, this is called an acid for a reason, Acids, remember, the basic definition of an acid is something that can donate a proton away. I can't remember whether that's the Arrhenius definition or the Bronsted-Lowry definition, but it's one of the basic definitions of an acid. What will happen is one of these hydroxyl groups here, either this one or this one, will donate a proton away. So what will happen is the single bond will break and both electrons will remain with the oxygen whilst the hydrogen will go off without any electrons, so it will just be a proton effectively. So what will happen, to draw the final step of this, is you will get a bicarbonate anion, which is carbon double bound to oxygen, single bonds to an oxygen which now has a negative charge, so that's the one that kept both of the electrons from that bond, and then you've got the proton going off, and it now has no electrons. Okay, so those are the two final products. So this is the reaction that is actually going to occur, and the reverse can occur. So what can happen is bicarbonate anions can hit protons, become carbonic acid. So I'll just draw the fact that the reverse can occur, and then the carbonic acid can, instead of splitting up into a bicarbonate and a proton, instead it can split up into a carbon dioxide and a water molecule. Okay, so that's the way that this reaction occurs, and as I say, it does reach a dynamic equilibrium. The other important thing to know about this reaction is it does not occur spontaneously. Okay, it requires catalysis in order to form carbonic acid from carbon dioxide and water. It requires catalysis, and the enzyme that catalyzes this reaction is known as carbonic anhydrase, and it's present within red blood cells. So let me draw this. So I will just make myself a little bit more space. So where can I go? I'll go up, actually. We'll go up here. Okay, so if I draw a red blood cell, so let's say this can represent a red blood cell here, and inside the red blood cell you have proteins, and of course one of the major proteins is hemoglobin, but we'll come back to that. The protein that we're interested in at the moment is an enzyme, and this is the carbonic anhydrase enzyme, and for short, carbonic anhydrase is often abbreviated down to Ca. So this is carbonic anhydrase. So of course the blood has a huge number of red blood cells in it, so therefore there's going to be a lot of carbonic anhydrase within the blood because it's inside the red blood cells. And I'll just label this up as an RBC. So this is a red blood cell, or an erythrocyte if you want to be fancy. Okay, so what will happen is carbon dioxide molecules and water molecules will go into the carbonic anhydrase enzyme, and then bicarbonate and proton will come out. Or alternatively, bicarbonate and protons will go into the carbonic anhydrase, and carbon dioxide and water will come out. Okay, this is the enzyme that's catalyzing that. So, overall then now, the message is that when we've got carbon dioxide dissolved in the blood, it's going to be in equilibrium with bicarbonate anions that are in the blood and protons that are in the blood. So I want to complete this discussion now by telling you what is the bicarbonate concentration within the arterial blood and what's the proton concentration within the arterial blood. Right, so we'll start with bicarbonate concentration. The normal bicarbonate concentration in the arterial blood is 24 millimolar. Now, this is actually also pretty much the concentration of bicarbonate in venous blood. As we'll discuss in just a moment, there is a slight difference in bicarbonate concentration in arterial blood and compared to in venous blood. However, it is only slight, and it doesn't really affect this number, so it's not significant enough to change this number. However, it is important that we know about it, and I'll come on to that in just a moment. But you can take this value pretty much as the bicarbonate concentration, or the approximate bicarbonate concentration in both arterial and venous blood, although as we'll discuss, in each person there is a difference in the bicarbonate concentration in arterial versus venous blood. Specifically, it's higher in venous blood because of course carbon dioxide is higher in venous blood. But we'll come on to that again in a moment. But as I say, it doesn't really affect this number. I mean, the number would go up, but it would be, it wouldn't be changing up to 25, it would be a tiny little change. So for all intents and purposes, you can take this as the concentration of bicarbonate in both arterial and venous blood. Okay, the other thing is the proton concentration. Now, of course, no one talks about proton concentration. Instead, we talk about pH of the blood. And I'll just remind you that the definition of pH is that it is the negative log, and this is log to base 10 of the proton concentration. It's one of the only places where you ever see log to base 10 used in pH. Log to base E is obviously the one mathematicians love, and it's a far more powerful logarithm than log to base 10, but we still use log to base 10 here. Now, a reminder of what this relationship means. This relationship means that actually, as the pH gets bigger, so if you go up, make this number bigger, say going up to 14, the proton concentration is actually getting lower, okay? Because of this negative and also because of the fact that we've got this logarithm here. Whereas pH getting smaller actually means that the proton concentration is going up, and everyone always gets confused about that. Everyone's always like, proton concentration is going up, therefore pH is going up. Wrong. pH goes down. pH going down means you're becoming more acidic, but it means the proton concentration is getting higher. Okay, so what then is the pH of arterial blood? Well, the pH of arterial blood is usually quoted as being around 7.4, and both of these are really estimates, they're averages rather than exact figures that the body must obey. And again, although it's important to be aware that there is a pH difference between arterial blood and venous blood, specifically venous blood has a lower, more acidic pH than arterial blood, the number is not significantly going to change, so you can take this again as the pH of both arterial blood and venous blood. Right, okay, so in arterial blood then, we have carbon dioxide dissolved. The partial pressure of arterial carbon dioxide is around 40 millimolar, and we now know that that dissolved carbon dioxide within the blood is going to be in equilibrium with bicarbonate and protons, and we know the concentration of bicarbonate and the concentration of protons, because you can easily from this get the concentration of protons. Just take the negative of the pH, so negative 7.4, and then raise it to the power of 10. So the proton concentration is 10 to the negative 7.4, and I'll just write that down. So actual proton concentration would be 10 to the negative 7.4. That's the way of rearranging this equation for pH. Okay, we've discussed the concentration of bicarbonate and protons that that dissolved concentration of carbon dioxide would be in equilibrium with. Right, so it is now time to actually discuss transportation of carbon dioxide around the bloodstream. We've discussed all the complicated bit now just by studying the arterial blood. Now let's go to the easier bit. Okay, so this is where we go back to the diagram that we drew in the original video, so I'll bring it up here, larger. Okay, so let me get my laser pointer. What's going to happen then? The arterial blood is going to go through the peripheral capillary. And what's going to happen now? Carbon dioxide is going to come from the tissue fluid into the bloodstream. Now, why is that going to occur? Well, it's going to occur because the carbon dioxide concentration in the tissue fluid is higher than the carbon dioxide concentration in the arterial blood. So, let me give you what the carbon dioxide concentration in the tissue fluid is going to be. And we'll use this as an opportunity to practice our understanding that we can talk about partial pressures of carbon dioxide dissolved in fluids rather than the actual concentration. So I'll firstly give you the actual concentration. So the actual concentration then of carbon dioxide in the tissue fluid is around 1.5 millimolar. And remember, the concentration in the arterial blood, and I'll just go back to it, that was 1.2 millimolar. So this is a bigger number, okay? It's higher concentration of carbon dioxide in tissue fluid at the peripheral tissues than it is in the blood that is coming from the arterial system here. Now let's just practice using partial pressures rather than absolute concentrations. So if we wanted to do this in terms of partial pressure, we could say that the partial pressure of the in the tissue fluid of carbon dioxide is, so a bit of maths now, what partial pressure would we need in order to get this concentration? Remember, the solubility is 0.03. So if I multiply 0.03 by 10, I get up to 0.3, and then of course 1.5 is 5 times 0.3, so I think the partial pressure is going to be 50 millimeters of mercury. And remember, the partial pressure of the arterial blood or of the alveolar gas was 40 millimeters of mercury. Okay, right. So because the concentration of carbon dioxide here is higher, what's going to happen is carbon dioxide is going to move by diffusion into the arterial blood that is moving through this peripheral capillary here. And that means that the concentration of carbon dioxide is going in the venous blood is going to rise up to be the same as this. So I could change the TF here for tissue fluid to V, and in fact I will now do this. So I'll just make a little bit of space for myself. I'll do it here. Okay, so if I, oh, whoops, let me get my pen back. So the concentration of carbon dioxide then in the venous blood is going to be the same as it was in the tissue fluid because they've equilibrated with one another. So it's going to be 1.5 millimolar, but of course we don't like talking about that because everyone has their different preferred concentration units, so instead we'll have the partial pressure of venous, so I've put a little subscript V there, CO2 is going to be equal to, and we'll have 50 millimeters of mercury, which is the partial pressure of carbon dioxide that the blood would need to be exposed to at 37 degrees Celsius in order to get that concentration of carbon dioxide here. Okay, right. So the dissolved concentration then of carbon dioxide in the venous blood is higher than it was in the arterial blood. Right. Now, of course, that's going to have an effect on the equilibrium that we've just discussed. If we have just raised, I'll go back to the laser pointer, if we've just raised the concentration of carbon dioxide that is dissolved in the blood, then of course we're going to shift this equilibrium. In particular, it's going to shift to this side. We've got more carbon dioxide, we've got lots of water, I mean there's water everywhere, so what's going to happen is we're going to make more bicarbonate and protons. So in particular, and I'll add this onto my little tally here, and firstly zoom in. So what's going to happen, the bicarbonate concentration and also the proton concentration, they're both going to go up in venous blood, okay? And I hope you understand exactly why. It's because we are putting in more carbon dioxide and therefore the forward reaction, the rate of the forward reaction will increase. The rate of the backward reaction won't increase initially, so you'll break the dynamic equilibrium. You will make more of the products here. You'll make more bicarbonate and more protons. Now that means that the bicarbonate concentration and the proton concentration are going to increase slightly. However, as I spent ages telling you a few moments ago, it doesn't mean these numbers change significantly. It is important to understand that the bicarbonate concentration will be slightly higher in venous blood compared to arterial blood, and also that the proton concentration will be slightly higher and therefore the pH slightly lower in venous blood compared to arterial blood. However, it does not significantly change these numbers, and therefore you can take these numbers as being the same in venous blood. So if you're asked to quote what is the bicarbonate concentration in venous blood, you would still quote 24 millimolar, but you need to understand that it will be lower than in arterial blood. Okay, right. So bicarbonate concentration and proton concentration are higher in the venous blood, and that's important when we come on to discuss transportation of oxygen. In particular, it's important that the proton concentration has gone up, the pH has gone down, because that affects the protonation of hemoglobin, which affects its affinity for oxygen, the so-called Bohr shift. But we'll come to that when we come to it. Okay, so let's finish the story. So we're now in the venous system here. So venous blood then, here is the carbon dioxide concentration in venous blood. We know that bicarbonate and protons are slightly higher, so we've completed up our story. We now know venous blood versus arterial blood, but let's complete the cycle. So the venous blood will then go through the right atrium, through the right ventricle, and it will come to the pulmonary capillary. And of course here, this venous blood is going to be turned back into arterial blood. So what's going to happen up here? Well, we know the alveolar partial pressure of carbon dioxide, and I'll just write this again up here. Alveolar partial pressure of carbon dioxide is 40 millimeters of mercury, not 50 millimeters of mercury. So what does that mean? That means that carbon dioxide is going to come out of solution because the blood that is coming up to the pulmonary capillaries here, it's got this concentration of carbon dioxide, and that will be in equilibrium with 50 millimeters of mercury, not 40. So that means this is too high for this. So carbon dioxide will come out of solution and go back into the gaseous form. So carbon dioxide will come into the alveolar air spaces. Okay, and our concentration of carbon dioxide will go back to being in equilibrium with this. But what is the concentration that's in equilibrium with this? Well, of course, that's the arterial concentration. That's this concentration over here, 1.2 millimolar. So the concentration of carbon dioxide dissolved will go back down to this, and of course that will cause this equilibrium to redistribute. We've just suddenly pulled this back down. That means that the rate of the forward reaction is going to go down, and now the backward reaction will dominate. The equilibrium will break. Bicarbonate and protons will go back to becoming carbon dioxide and water, catalyzed, of course, by the carbonic anhydrase. You have to remember that. This is very important. If this was suddenly to disappear, then the equilibrium wouldn't actually shift in time. This reaction occurs ridiculously slowly without catalysis. So this is very, very important. So bicarbonate and protons will return to being carbon dioxide and water, and that carbon dioxide will then be given off and go into the alveolar air spaces as well. Okay, so we therefore move our bicarbonate concentration and proton concentration back down to what they were in the arterial blood. So bicarbonate concentration goes down and pH goes up. So you become slightly more alkaline than venous blood. And we're back at arterial blood. And there is the complete story of how carbon dioxide is transported within the bloodstream. So we'll have a break here, and then in the next video we will do the equivalent for oxygen.